Okay, problem 5 on the review is a pretty challenging problem. It's an SAT test preparation problem. It says in the figure above, first of all, it says the figure is not drawn to scale. So you can't sort of estimate measurements, you have to calculate them using Pythagorean theorem. In the figure above, AB is equal to CD. So in order to sort of show these two right triangles more distinctly, I've highlighted one of them red and one of them blue. But in both right triangles, the hypotenuse is 25, so the hypotenuse of each triangle are congruent to each other. EB is 7, that's shown on the figure, and AC is 4. AC is this distance from here to here. And we're asked what is the length of BD, this length right here. The first thing we can do is, if you focus on the red triangle, we were given that the hypotenuse AB is equal to 25. So this is 25, and this is 7. So we know one leg, and we know the hypotenuse, so we can try to find B, which would be the other side of this red, the other leg of this red right triangle. Using that Pythagorean theorem, a squared plus b squared equals c squared. Again, a is 7. So 7 squared plus b squared is equal to c squared, but c is 25. 7 squared is 49. 25 squared is 625. If we subtract 49 from both sides of that equation, we get b squared is equal to this difference, which is 576, which happens to be 24 squared. So b is the square root of 576, which is exactly 24. So if this entire leg is 24 and this piece is 4, then on the blue triangle, this leg EC must be 20. This leg right here, because if this is 4 and this is 24, this must be 20. What that does for us now we have one leg and the hypotenuse of the blue triangle. And so we can use Pythagorean theorem again, a squared plus b squared equals c squared. The leg that we know is 20 squared. We don't know the other leg, but we do know the hypotenuse is 25. 20 squared is 400. 25 squared is 625. Subtract 400 from both sides of this equation, and you get b squared is equal to 225, and the square root of 225 is 15. So that means ED is 15, and if EB is 7, BD must be the difference between 15 and 7, which is 8. So answer choice E. Don't forget, if you're watching a video, you can always pause it. You can go back a little bit if I'm going too fast. Problem number 6 asks us to convert this number in standard form to scientific notation, and then this number in scientific notation to standard form. In order to convert to scientific notation, we should rewrite the number without the commas. And I'm going to show where the decimal is right now. This is a whole number, so the decimal's on the right. Then I'm going to decide where I want that decimal to be. I need my first factor in my scientific notation expression to be greater than or equal to 1, but less than 10, so I need the decimal there. So I have 3.4502. Times 10 to the what? We'll figure that out next. But we know it's going to be some positive exponent because I'm dealing with a very large number, a number much larger than 1. If I take the decimal from where I want it to be to where it really is, I'm moving it 1, 2, 3, 4, 5, 6, 7, 8 to the right. So it's 3.4502 times 10 to the positive 8. Okay, to convert 4 and 2 thousandths times 10 to the negative 4th to standard form, we write down the first factor, 4 and 2/1000ths, and then we recognize that multiplying by 10 to the negative fourth is like dividing by 10 4 times. We have a very small number if this is a negative exponent, so my decimal moves to the left 4 places. 1, 2, 3, 4. Wherever it lands, I make a big decimal so I remember that it's there now. And then this is just like filling in an egg carton with eggs. I'm putting zeros in each of these little spaces to represent zeros for those place values. Then I rewrite the number, it's decimal, and then 3 zeros, and then the 4002. And it's good to put a leading 0, but it's not required. Okay, problem number 7. Plot these ordered pairs. As you plot these points, label them and connect each new point to the previous point by drawing a line. So, just trying to pick the best color for this. A is at 0, 0. That is the origin. And so I don't need to move right or left. I don't need to move up or down. My point's at the origin. I'm going to name that origin. And I'm going to label that point A. Point B is at 0, 4, so I start at the origin. And then my x-coordinate is 0. Remember, it's always x before y. X is 0, so I don't need to move right or left at all, but y is 4, so I need to move up 1, 2, 3, 4. So point B is here on the y-axis. Point C is at, oh no, I'm supposed to draw a line between those, so let's do that. Point C is at 2, 0. So the first coordinate is x, so I start at the origin, and for positive 2 I go 2 to the right. Y is 0, so I don't need to go up or down at all. My point is right here. Connect that to the previous point, and I'll connect these. That's point C, and C is on the x-axis. The most specific name for the polygon we've drawn, we've drawn a triangle. It has a right angle, so it's a right triangle. And all the sides are different lengths, so it's right scalene triangle. The area will be found using the area formula, 1/2 base times height. So the area is 1/2 multiplied by, I have a base of 2 and a height of 4. So area equals half of 2 is 1. So 4 units squared for the area. Problem number 8 asks for examples of each of the properties listed below. The multiplicative identity tells us that if we multiply anything by 1, it retains its identity, or it identifies the value that we're multiplying by 1. So 9 multiplied by 1 equals 9 is an example of the multiplicative identity. Multiplicative inverse tells us that if we multiply reciprocals, we get a product of 1. So 7 multiplied by 1/7 equals 1. That's an example of the multiplicative inverse. Substitution. A good example of substitution would be if I had an equation like 3x equals 9, and then I identified x as 3, I could substitute 3 for x. 3 multiplied by 3 equals 9 to verify the variable value. So this is a good example of substitution right there. The additive identity tells us that if we add 0 to something, it maintains its identity, or by adding 0 we identify the variable value. So 9 plus 0 equals 9. That's an example of the additive identity. Additive inverse tells us that if we add opposites we get a sum of 0. So as an example, 7 plus negative 7 equals 0, or 5 minus 5 equals 0. Those are both examples of additive inverse. The reflexive property can be seen here if I completed this expression where I find 9 equals 9. That's the reflexive property. It's like the value is looking at its reflection in a mirror. For property of equality, we could consider an equation that we're trying to solve. And if I wanted to solve this equation for x, I'd be trying to isolate x on this side of the equal sign. And so I would subtract 3 from both sides of the equation. That's property of equality. Anytime you do the same thing on both sides of the equation. To keep the equation balanced using that balanced scale model that we learned in class. Okay, that completes page 2. We'll continue the review with the video for page 3 on the next video. Thanks for watching.